Montana Tech is in a partnership with the University of Kashmir related to studying invasive plants and climate change in the Himalayas and in the northern Rockies. Robert Powell is the PI from Montana Tech, and Manzoor Shah is the PI from the University of Kashmir. Under that partnership, which is funded by the government of India, the group from the University of Kashmir visited Montana Tech in 2017. A group from Montana Tech visited the University of Kashmir and the Kashmir and Ladakh in 2018, and now we have the group back again. In the meantime, University of Kashmir acquired a new vice chancellor. For those who are not aware, a vice chancellor is like a president or a chancellor in the United States. The vice chancellor, the new vice chancellor, is Professor Dr. Talat Ahmad, and he is a very distinguished geologist. And he got his degrees in geology from a university in India that I'm sure nobody here who's not in India has heard of, unfortunately. But then he did postdoctoral work at the University of Leicester in the UK, at the University of Cambridge in the UK, and a third postdoc at the University of Nagoya in Japan. He's worked with the Geological Survey of India for a year or so, and visited the Montana Geological Survey this morning. And he's been in the Department of Geology as a professor at the University of Delhi for many, many years. He's been a vice chancellor at the University of Kashmir previously. Then he was a vice chancellor at the University
in Delhi, Jamia
Islamia, in Delhi, and now he's back as of July in Kashmir as the vice chancellor. He has received more awards, and he's a fellow of more professional organizations that are essentially equivalent to the U.S. National Academy, which is really quite distinguished. And we are really delighted to have him here to talk to us about the evolution of the Trans-Himalayan Ladakh terrain, constraints from Indus and Shyok Suture zones, because when we were there in 2018, we actually drove across and through those zones with questions appearing to us every kilometer.
Yep.
So welcome to Montana.
Thank you so much. Thank you so much. It's a pleasure to be here, and I look forward to visit the very famous ranges of this Rockies here. And then when last year when I met her and some other colleagues from Montana Tech, I was already knowing that I'm going back to Kashmir, and she was told that one can come and see, because I am basically trained as a geochemist, although basic degree in geology, and then I have specialized more in the geochemistry of basalts and hard rocks, and then did extensive work in Ladakh, which is the northern edge of the Himalayas, just cross the Himalayas, so it's called Trans-Himalayan. So I have tried to make a very simple presentation. I should also tell you that these are some of my collaborators from the Australian National University, with whom I used their facilities to date some of the rocks from the Ladakh Battle It. So as you can see here, this is part of the Ladakh terrain, and what you see here is these type of roads. So Brev and others, they have experienced, and you have to cross many, they will say la, which is the passes, where you have to breathe enough like a camel and store it for yourself to go and cross that. So, and on an average, the elevation here is about 3.5 to 4 kilometers. So the air is very thin, very low oxygen. So at least 2-3 days. This is the lowest point. This is the Indus River, about 3.5 kilometer high. So you have to be there for 2-3 days, just acclimatize yourself. And then you can start working. So what you see is we have, as a geologist, when I was working with the Institute of Himalayan Geology, we used to go with jeeps and trailers and all the food stuff, and so that we take back the rocks. And there was nothing. Actually, even now you can see that there is no greenery, nothing. Only greenery that has come is last 10 years or 15 years along this river bank, where people now have some farming, but no trees and no greenery is because of the height. So it's a very difficult terrain, but very interesting for geologists in the sense that there is no plant cover, or you don't have to actually remove if you work in other parts of the Himalayas, or then you have to first clean the whole area to do geology. But here it is all very exposed rocks. So what you see here is this is the Indus River, which is supposedly the junction between the Indian and the Tibetan plate, where the collision has taken place. This is part of the Ganges, or the Ladakh Battle It in Pakistan, they call it Kohistan. This side in China, they call it as Lhasa block. So there's about 2,500 kilometer long subduction related batholith. And then we have another range which is known as the Karakoram range. This is another set of batholith. In between this and this, there is another suture zone, which is known as the Shiok suture zone. So the Indus, you can see here, Indus suture is here, and the Shiok suture is there. So one batholith, another batholith, and then you have the whole set. So when we started working in this area, the earlier studies, they had put this suture zone and this suture zone to be related, because almost similar type of rocks. They were all basalts, and then obviously the granitoids, acidic volcanics on both the sides. But later, when we did more extensive work based on trace elements and isotopes, we could show that these suture zone from north and south, they were totally different entities and totally different tectonic setting. So I will explain as we go further. In general, for non-geologists, you can, I thought I'll just make it simple things. Like what we have here, these red ones are the mid-ocean ridges where new rocks are formed coming from the mantle, and then these continents, they get separated and the oceans open up, and then from here to here it takes about, or from here to here, it takes about 200 million years. So you don't expect rock to be more than 200 million years on any ocean floor. So all the old rocks have to be preserved on these continents, which are much lighter and buoyant. You can see here in this cartoon that the new material comes, and this goes this way, and ultimately from here, 0 to 200 million years, it goes back to the mantle. And as it goes down, it gets heated up, and you have lots of arc or volcanoes, which you all know. You can have volcanoes here, which is, you have this continental material and then put this ocean floor. You will have also oceanic arc, which is where one part of ocean is subducting under the others, like Mariana Arc. So we have two types of arc, and fortunately for us, we could identify both these arcs present in Ladakh. So there's the simple thing I was telling you. So this is a typical continental arc where you have this ocean floor going down. This is the continental crust. So you have these, which is very commonly seen in any continental arc or arc in such. And this is the ocean floor, and ocean floor, you have another set of arc, which is more towards the Mariana type, and this will be more like the Andean type. Okay, now about the Himalayas, how it has come into being. If you see, we all know that we have the Gondwana land, and then we had this ice mass which was present, and then the oceans opened up. So we have preservation of these material, which were during the ice age, and have the presence of Glaciopteris and other fossils indicating that this part of the continent was having similar. And then you have all these areas are very good deposits of coal. In general, the Gondwana coal fields are all present, whether it is India or Australia or South Africa, South America. Okay, there's another cartoon which shows that they were together. We have in front of India an ocean which is known as the Tethyan Ocean, okay, which is at present not there. It was like Pacific, where you have all types of seamounts and mid-ocean ridges and things like that. So say about 160 million years, this is a cartoon. If you see 100 million years, that means this Indian Ocean started opening up. These things have moved in different direction, and India is moving further north. And these are some of the slivers which are now present as Omanophyllite, for example. And then around 55, we have very well developed Indian Ocean, and we have come closer to Eurasia, but still these slivers are there. So in literature in general, there is, there was lots of information that the collision actually occurred around 55 million years or 50 to 55 million years. But with more data that we did with Australian National University, we know that 55 million years used to be a very big event. But there is nothing like one collision. It used to be a series of accretion. So 55 million years to be one of the big events like that. And you can see in 3 dimensions, what I was telling is as you open up the Indian Ocean, India moves, but it goes, some part of it subducts within the ocean, and the other goes beyond and gets subducted under the Eurasia. So this is the greater India, you can see. Okay, so ultimately when there is collision, so the collision is not simple that you just collide, but part of India goes under the Tibet, and then you raise this whole thing as fold and fold mountain bed, and then wherever there are pressures, there are also release of pressures through these fractures, and you have famous earthquakes. They are recorded along these areas. Okay, and this is a very common slide where you can see India has collided. This is the Indo-Australian plate. So still the Australian side of the plate still subducting in this Andamans and other parts, and you have, so what we see here is all these black dots that we see and the red ones are the areas which are seismically very, very active, and subduction is taking place here. So that was a very generalized thing for those who are non-geologists to understand that from where India was and where we are now. We have gone across the equator from near the South Pole to north. Now this is a sort of map of the Himalayas, which is divided from south to north into the Sevalics, or the very, very young tertiary rocks. Then we have the lesser Himalayan rocks, which has lots of volcanics and also sediments. These are going from Precambrian, so say 2.5 million years up to Cambrian. Then we have the central Himalayan. There is the higher Himalayan crystallines, they call, which has very high-grade rocks, mostly gneisses. Earlier, people used to think that the Indian shield goes under and then comes back as these ones, higher Himalayas. But our data has shown that they are much younger compared to this. So this is actually not the Indian part of the Indian shield, but it is a sort of basement for these rocks, which are the Tethyan sediments. And then finally, we have these ophiolites present all over, which preserved part of the Neo-Tethyan Ocean that was available. And then I will be concentrating more on this area to show you how things are. So this is a map where you have this Ladakh Battle It, and this is part of the Zanskar or the Tethyan sediments. Here, these are some of the rocks, which are again the basement rocks, very famous for presence of coesite and microdiamond, indicating that part of the Indian crust has gone to the depth of at least 100 kilometers and then abducted. But it has to abduct very fast and to preserve that microdiamonds as microdiamond, otherwise they will go into coal. Okay, so but they are entrapped in sort of barrels of zircon and garnet. I'll show you some of these. This is the Suture, the zone. You can see that these rocks are volcanic censured here, and then ultramafic. These are the melange rocks where everything gets physically mixed up. So you have the oceanic material which is present here, and then this is a series which we have shown them to be part of a whole arc from the bottom. It is more ultramafics, then gabbros, and then the volcanosedimentary sequence. So this sequence and this sequence, people used to think that they are similar, but I will show you the data indicates that they are totally different. And then we have dated these rocks, and they are shown as one mass, but actually there are at least 5 to 6 phases of magma that has come and intruded into this batholith. And same is the case with this Karakoram batholith. Okay, I was telling you this is part of the Indus River fan, where people have now greenery. Maybe now I will find out from Professor Zafar and Professor Manzoor, are these invasive? Because there was nothing earlier. So people brought this from somewhere and planted. And then this is the batholith. You can see that beyond these riverbeds, there is no vegetation. Okay? This is just a geotourism. Here on the Ladakh Battle It, you have these gompas where these Buddhist monks, they are trained and they get educated. So these are some of my collaborators. They are going to see the rocks and also go into this monastery. You can see the Buddha, huge Buddha. I mean, you can go in 2-3 floors to see the whole Buddha in those monasteries. If you really want something in your life, you turn to this circle and think what you want. If you're lucky, you may have that. Okay, so they are all available. Maybe not in Montana, but in Leh. So you have to come in. And then obviously, yesterday, when I was here, and Doug took us to the fair, and we could see how the village people enjoy once in a year, getting together, because again, there the population is very sparse. So they get any chance, they try to get all together with some of these local musical bands. Okay, so now what you see is this is the Zanskar Range. Zanskar Range is the south of the Batholith, and the suture zone has to be here. So I have taken this photograph from Ladakh Battle It, and you can see that this whole mountain range is covered by snow. When you come in just south of the Batholith, okay, this is the suture zone. What you see here is spectacular sedimentary sequence, which is known as the Indus sequence, where you have the clasts from the Ladakh Batholith. So it shows that the Ladakh Batholith has exhumed and shed off these sediments. When you go south, you see that you have clasts coming from the material from the oceanic arc. Okay, so this is a hazy picture of the Ladakh Batholith. Okay, and so they look very monotonous as such. But when you go closer, you can see that you have lots of variation. And for the students of geology, these are very interesting features. These are actually showing magma mingling, in the sense that the batholith was still cooling, and it was about 80% cooled and crystallized, but still 20% fluid, and you bring another magma. So it doesn't mix, because this is diuretic, it is much higher temperature, so it forms blobs all over, as you know, because if it was 100% cooled, then you will form dikes, which will be one thing. But since it has not cooled and you bring new material, so you have these blobs, which is known as the magma mingling. Okay, so again you can see that one rock and there's another rock, both of them are compositionally similar, but they have different, one cutting through the other. Okay, so all these things indicate that the whole batholith has not come in one go, but it has come in different phases. This is one of the highest motorable pass. I hope you have gone to Khardungla. It is about 7 kilometers high. Okay, so 6.8 is here. This is 7 plus, means 7 kilometers above the sea level. So you can imagine here, and still we have cars who are specially tuned, okay, to go there. Otherwise, your cars won't go there, nor our Delhi car will go. Okay, and then we also have very interesting foreign tourists. They take these BSF, the big bikes, and they go on that. It's a very interesting tourist area. I'm also trying to attract these younger people to come to Ladakh, because these people will come, but they need more hands, and we need more people to come, and it's a huge area to cover. Okay. Then this is the last phase of the batholith, which is more of apletic vein. They have been dated about 21 to 18 million years. So we think that these are related to the movement on the Karakoram fault, which is there, and these are more of a S-type granite, means the granite which is formed by melting of the sediments, rather than the granite which comes from the mantle or subduction zone. Okay. These are some of the things which are part of the ocean floor. These are the ophiolitic rocks. Okay, they are also known as colored melange. And then you can see here, I was telling you, eclogites. These have micro diamonds in that, indicating, and they are actually basic material. At present, it is eclogite. Originally, it should have been basalt or basic dikes, which has gone to the depth of 100 kilometers, got the micro diamonds and came back. So you will have lots. You can see some of these dikes or enclaves are so big. This is one of our students. for scale. So you have these, as well as you have even smaller ones. So they are all over, indicating that when it is coming, don't think that it will come from 100 kilometers depth, abducted, and it will be sleeping. It is just breaking and shattering and all sorts of physical mixing. So you can see same sort of things all over. And then you have to study these to show that eclogites, now it is very well studied. So the 55 million year age has come from these, indicating that at 55 million years, definitely things were happening, that it has gone to the depth of 100 kilometers, got it metamorphosed, and then got it abducted. Okay, so these were some of the, and then obviously now things are better, but initially we used to have this sort of camps, very beautiful. You have to just zip your camp and go. Nobody will be there to, like Montana, maybe in far off places, there will be nobody to come and open your tent.
No bears.
No bears. Only Hanguls may come, but not Hanguls. There are some blue sheep herds, but they won't come here. And then obviously we have tents for cooking and tents for eating and for sleeping. Now this is a cartoon which shows what I was telling you is this is the Ladakh Battle It. This is the Suture zone. So when this thing has come up, it has shed sediments. So you have lots of clasts within these, in this. And here we have dated some of these clasts, which has given a mica age of 12 million years. So indicating that at 12 million years, things were active in terms of shedding of sediments. Okay, same map as I showed you. So now I'm going to show you some chemistry of rocks from here and rocks from here to clarify that these rocks are very different from these ones. So what you see here is this Nidar, and these are mostly from the southern suture or Indus suture. So Indus suture, you have from basic rocks to very, very acidic rocks, but there is a compositional gap. So these are known for the geologists, they know as bimodal volcanism. So you have both acidic and basic rocks erupting together with a compositional gap. Okay, so you can see this with different, like you can see again with respect to silica, again you have this difference. Okay, even in terms of the ratios of niobium, yttrium, or zirconium, you can see very easily that there are two group of rocks which are present in the southern suture, and also with respect to the strontium isotopes you were telling. And then what you see is the gap is there in terms of the major elements, but when it comes to the isotopic ratios, so this is for neodymium or for the strontium, they are almost similar, whether they are acidic or basic. So indicating that they have been derived from similar rocks in terms of sources in terms of their isotopic ratios. Okay, so they were part of the arc that was melting. So deeper part was giving you basic rocks, and the shallower part was giving you the acidic rocks. Okay, now if you see the rocks from the northern suture, this is Nubra or the Shok. So you see going from basalt to rhyolite or dacite, you have a continuous variation. Okay, there is no gap here. Okay, so you can see whether you take with respect to silica or the ratios of these incompatible trace elements, they show that there is a continuum. So both these are very different. And when you see the rare earths, I was told that rare earth is a now very fancy thing here in Montana in terms of mining they're looking for. So if you see the rare earth, they are mostly flat. For the gabbro, for the volcanics, for the acidic volcanics, they are all flat. And when you see with respect to rare earth, this northern suture, they are enriched. See, this is the light rare earth, the heavy. So you have a higher LRE by HRE variation. Okay? So these ones are from the southern suture. These ones are from the northern suture. So now you can imagine they cannot come from same sort of sources or same sort of tectonic setting. So what we think is that these represents the Mariana type or ocean-ocean subduction related arc, and this is ocean continent, because ocean continent, that part of the Tethyan Ocean was subducting under the southern Tibet, which was a continent. So there was interaction with the magma and you make these more enriched. Whereas here it is one ocean material interacting with the other, so you don't see any enrichment of the rare earths. Same thing, you can see that these are niobium and phosphorus, and so all these trace element ratios indicate that these two are different, and these ones are more related to ocean continent system of arc, or the Andean type, and this is the Mariana type. Okay, even another important thing that came by these studies, if you see that these are mostly from the Indus suture, so these are the Didar, all the rocks which I was showing you. This is the melange rock. So in melange, what you see here is they are different than these in the sense that you have zirconium-yttrium ratio showing large variation, whereas the zirconium-niobium is very little variation. Whereas these rocks, these arc rocks, they show large variation in terms of the zirconium-niobium ratio, but very little in terms of the zirconium-yttrium. You all know that yttrium is controlled by the presence of garnet at depth. So when you are bringing rocks from deeper sources, the ocean island basalt type, then you should expect this type of distribution. And this is the distribution you expect when it is the arc, because they are mostly shallow, so you don't have garnet in the source. Now, if you see the western part, in the western part, again, western part of this Shergol and other part of the Indus suture, you have the same sort of arrangement. And all these things are now reduced to this green color, but you see this yellow color is from this sediments from the Dras arc. So you have same distribution whether it is eastern Ladakh or western Ladakh. Only difference is what you see is this one, blue one. So these are the ones which are from the northern side. So they are totally different with respect to these, with respect to these. This diagram also proves that within the ophiolite zone where we have preserved the oceanic crust, we have arc-related rocks, we have mid-ocean ridge type rocks, and we also have oceanic island like what you have in the Hawaii. So whatever we see now in the Pacific was present in the Tethyan Ocean that time. Okay? And whatever we see now in the southern part of South America, that the Andean type was also preserved in Ladakh. So we have everything there. Okay, we have also dated these using mineral and whole rock. Sorry, these are the minerals, pledge and pyroxene and whole rock. So you get a 9-point isochron age of 140 plus minus 32, which for these younger rocks, this is the best possible date that one can expect using samarium neodymium. But we also did some work with the Japanese, as I was you were told that I worked with some of the Japanese who are very good in radiolarian fossils, very precise. So they have also, don't ask me the names, it's very difficult. And that too with Japanese authors, you can understand. So, but beautiful fossils, microfossils, all these have given the similar age of 112 million years. So they are in the radiolarian chert fossils. So you have the basalt and gabbro, which has been dated 140, and on the top of it, you have 112 million years for these radiolarites. Now, same diagram, now I will show you data that we have generated from the batholith. Okay, so first of all, you see that they are going from granite to monzonite, to granodiorite, to tonalite. This is the compositional variation. We have data from Ladakh Battle It, and also we have taken from China, this Yang Beijing and Lhasa. So what important thing that you see is that from here to here, this is a AFM diagram, which indicates that they are following the arc type of or subduction related magmatism. So whether it was Chinese rock or the Pakistani rock or Indian rock, everything faced the same sort of subduction setting and giving rise to these Ganges belt as it is known. We also have data from Pakistan in terms of the ratios of strontium and neodymium. They are all falling within the arc. And these are again some part of some from India and some from Pakistan. And you see that we have the arc component present. We also have the more what is present at present in the Pacific or Atlantic was present in the Tethyan Ocean. Now we dated, as I told you, that 55 million years used to be thought to be the age of collision between India and, but now we see that we also have rocks which are 31. These are zircons, separated zircons. So you have 31 and then you have again 31. So what we have, this is all published. See, this is, for example, 25, 57, so 50, and then you see more data. You have all sorts of variation, okay, 64, 66, 50, 59. So now what you see the distribution, what you see is that we have in Ladakh Batholith rocks ranging from 70 to around 50, 45, then some 40. Then you have another big number around 18 to between 10 and 20, 25. This is the younger one. I was showing you the sort of dikes, white dikes, aplites. So they are the last phase of the batholith, which was post-collisional, after collision. Whereas these are all active accretionary process in the formation of Ladakh Batholith. You see here, there is more data which indicates that around 32 million years, we feel that 32 million years was the terminal age in terms of the last collision. Okay. Same thing, you can see that huge database from say 65, 70 goes to 50. You have big peaks, another peak around 50, 55, and then 45, and then this bimodal distribution. So which all indicate that the collision of the Himalayas was not one event at 55, but it used to be a series of accretionary event, right from 70 million years to even 90, 100, 110 also some people have reported, but we got only up to 90. So from 90 to 45 with the big event around 55. Okay, and then this is after the collision, we have this S-type or the sedimentary type granite, which is because of the thickening of the crust. Okay, and then the data which people were somehow they were not able to convince that there can be ages beyond 55. Now, after we published, we see lots of data being published all over the Himalayas, whether from Pakistan to China. You have dates around 32, 32, 44, 32, 32. So we think that the 32 was the real terminal age in terms of the collision. Okay, the model that we gave was that this is the Indian plate, the Tethyan thing, and this is part of the Tethyan Ocean. So this is the oceanic material. So ocean subducting under ocean, giving rise to the southern suture, that is in the suture. And this is the same oceanic material undergoing subduction with the southern Tibet, which was a continental thing, so which gave rise to the Andean type. So we have both Andean type and Mariana type arc. This thing closed at about 75 million years. This thing continued. So at present what we see is this: one suture zone, another suture zone, one batholith, Ladakh Battle It, the Karakoram Batholith, Tibet or the Eurasian plate in the north, Indian plate in the south. Okay, this is the present configuration. You will always have lots of friends when you are in the field. They will be always there and enjoy your bonfire. Thank you so much. So they are exciting places to come. Yep.
Questions? So I'll ask a question to start off. So India running into the Eurasian plate is one of the few locations where a continent is running into another continent.
Yes.
As opposed to you just have ocean floor.
Ocean, that's right.
Below
Yeah.
the continents. What are the biggest differences geologically between those two subduction types?
See, the thing is, it is very uncommon to push continent under continent. But it has started only after 32 million years. Before that, it was the big Tethyan Ocean which was subducting under the continent, southern continent. And then there's something called slab pull. So that huge ocean floor of few thousand kilometers has gone down, and then the northern tip of the India is being pulled. Okay, but if you see one of the diagrams that I was showing you, where the ocean is going under ocean, like near Japan or Sumatra, the subduction is much faster compared to what we have now, where we have the continent and continents. Very, very slow process. And lots of breaking, lots of seismicity that is happening. So you can expect much shallower seismicity when you have continent undergoing continent. Whereas deeper seismicity is where you have the ocean going under the continent. And obviously, one place you will have is the formation of Mariana type arc, where you have the ocean undergoing subduction to another, and the Andes type, what best is in the Andes, where you have the ocean undergoing the continent, and different types of arc material. And obviously, in terms of the trace elements, maybe he will understand better, is that both the oceanic lithosphere and the continental lithosphere are very different geochemically. So when you subduct one ocean under the other ocean, both of them are similar. So you're not going to change the chemistry much. Whereas if you have a thick continental crust and you put a subduction of the oceanic crust, the material is going to interact with such a thick continental crust. So the ultimate material that comes out as arc is going to be very different. It has lots of signature coming from the continental material.
I guess I have a question too, and it's similar to this, but can you go back to your model?
Uh-huh.
Slides?
Yes. Yeah.
And as I look at that, I'm trying to see where is the continent of India as it comes in and finally collides. Is it not, you just don't see it on the scale?
No, not on this scale.
On the scale?
Yes, because the India was behind this side, because this is about say 140 million years. Okay. Now I can get your point. So here it becomes Indian plate. I don't say the oceanic crust. So now the present you have the Indian continental material going down. Okay, up to here, this is the part of the Tethyan Ocean. Right? Here what you have is the subduction of the Indian crust or the Indian lithosphere. And if you see other models, beyond this, further south, you have abduction of these material on the top of the, you have all south vergent thrusts in which the material, younger material going and sitting on the older material. If you go to the lesser Himalayas or the higher Himalayan crystallines. Yes.
About that, isn't there a change in virgins as you go from south to north? Like in the Ladakh at the Karakoram Battle It, was that thrusted the other direction towards the north?
See, what happens is, at present now everything is thrusted south. Okay, the subduction was going north. Okay, but ultimately when it is colliding, okay, you have south vergent thrusting all over the Himalayas. So initially it was more north vergent subduction, and later after the collision everything is now going south vergent in terms of the big thrusts, the main central thrust, main boundary thrust.
Isn't there a place where the top is going top towards the north?
Top towards the north is in the central part of the Himalayas, the higher Himalayan crystallines, where there is a sort of splay, and you have a normal faulting of the material of the higher Himalayan crystallines, and this is the Neo-Tethyan Ocean. But many places this thing has gone up and then come down. So you have all the now these leucogranites coming through them because of the release of pressure. That is no. This is much north. Yeah, that is much south. Yeah.
I have another question about the zircons. Are those detrital zircons or igneous?
No, they are igneous zircon. They are all igneous zircon, except for one or two zircons which has given us an age of 870. Which is Gondwanik. So whether it was, it must be inherited either from the southern edge of Tibet. Okay, so that was inherited in the granite which came up. But otherwise they are all igneous.
So you mentioned a formation, I apologize, I can't pronounce it, SWI, the younger clastic sedimentary. Has anybody looked at it geochemically to see how much it's coming from the igneous uplifted areas versus the eroded?
In this part of the Himalayas, in the Ladakh?
Farther down into the basin, just taking what you've learned.
Right. So yeah, there are actually, if you see the sediments which are present in the Sivaliks, okay, Sivaliks for example, they are coming from both sedimentary derived from the older sediments, right, or the Precambrian sediments, as well as there are indications of also getting material from the ophilitic material. Okay, because you have lots of chromite, which has been.
So it would be chromite that would be the.
It has to be in the northern part, from the ophilitic zone.
Okay.
Yeah. So there were channels which was actually transporting sediments as there were lots of south vergent thrusts. Material were going, so even the part of the ophilitic material has come through them to this. But mostly it is sedimentary derived. Yeah.
Okay, so the Karakoram batholith is an igneous intrusive
Yes.
that formed as a result of the ocean crust going under
Under
Asian
the,
plate,
yes.
under the Asian plate.
Yes.
So that would be somewhat similar to Alaska.
Alaska, yeah,
or,
yes.
the
So the
Washington Cascade.
right. So they are mostly continent ocean type batholith.
And so then the Ladakh batholith, which doesn't exist being called a batholith, although it has the same coloring, and it's called the Kohistan Ladakh, and then it says
Yeah.
the Kohistan Ladakh Arc.
Yeah.
And then at the bottom it says the Kohistan Ladakh batholith.
Yeah.
Are those all intrusives already, even when it's like so far apart?
No, but they are not apart. They are part of the big system.
Yeah,
So
right.
there is continuous batholith.
But they're associated with the Indian plate at that point was just oceanic when it was creating it. So it was oceanic running into ocean,
Yes.
and then.
And same thing was happening in Kohistan.
Okay.
Yeah.
But in Kohistan already it was the Asian plate, so it was.
Kohistan was
No,
part.
that's Karakoram.
This Karakoram.
Yeah, so, but now you have the Indian plate, which has the continent on it, being subductive. I'm curious about the mineralogical or chemical differences between the Karakoram batholith and the Ladakh.
See-
Batholith and Ladakh batholith seem to have two phases, a continent-continent collision and ocean-continent or ocean-ocean collision.
No, so Ladakh Batholith, when Ladakh Batholith formed, it was just ocean.
Okay?
Yeah. Later, this thing has come, continent has come much later.
The continent came much later.
Much
and has
later.
nothing to do with
No. That was closed by 45 million years. Okay? It exhumed around 12 million years. Okay? So it was all oceanic arc.
Right. But there must be differences between.
There is
the
difference.
batholith and
That is what I showed you, the data. The Ladakh Batholith and Karakoram Batholith. Karakoram Batholith is more enriched. All the material in Karakoram Batholith shows the interaction between continent and ocean.
Right.
Whereas in the Ladakh Batholith, as I was showing you, even the isotopes, there is no enrichment. They're showing the same thing.
Yeah, okay.
Yeah? And these things are now very, very late when this Indian continent has started going down.
But now, so if you were drawing right now on your present, where is Srinagar? It's on the,
the-
it'll be on the bottom. It's on
this-
the bottom.
this is
It's on the
north-south.
It's on the bottom one. You have to, Srinagar with the present, you need to use the bottom.
Yeah, but the thing is, this is a model which is north-south. And Srinagar is much west.
West.
Much
Okay,
west.
this goes-
And then Srinagar has its own complexities.
Okay.
It is not only politically, but geologically. Geologically also, you have many material missing in this when you go from, say, for example, Jammu to Srinagar, or if you go from Himachal side to Ladakh, there is a big difference because of the presence of Panjal traps, for example, which is not there everywhere. Okay, so Abhi, this is more for Ladakh area, but for Kashmir area, the tectonics is totally different, and it needs huge work actually. So because of that, I am inviting you people, and also people with geophysics background, because we need lots of information, what is happening, where things are missing.
Right, so you're going to take your instruments?
Yes.
Yeah.
Yeah.
I was looking at your zircon distributions, and it looks like you have a lot of magnetism going back to.
At least five major phases.
Right.
Yeah.
Would you mind going back to that slide? Just so I understand it.
Yeah, this one?
Yeah. So you have all that subduction related volcanism, which
Up to here.
up to here.
Yes.
And that's where
Then yeah, and then this is the one, you are familiar with that area. You have the Karakoram. So Karakoram fault got reactivated around 21 to 18 million. If you see paper by Mike Searle also, they got the same sort of thing. So up to here, earlier people were thinking the collision is only up to here. Now what we see is that this is one accretion, another accretion, third accretion, fourth. So it is a series of accretion rather than one collision. And the terminal collision will be here.
Right. And so after the terminal collisions, you have that additional phase of volcanism. which
This
is
one.
10 and 20.
Yeah.
What do you attribute that to? And what do you
To the reactivation of Karakoram fault and the thickening of the continental crust, okay, which gives rise to the S type of granite, the sedimentary type of granite. These are mostly I type granite. Okay?
Thank you.
And similar things in your area, you have the same ages, even younger, further north.
Yeah, 1 million-year-old basalt.
Yes. 11 is another big date that is coming around in Tibet. And then obviously very young ones are 1 billion year. Some of my colleagues from Open University, Nigel Harris and his students, they were working in the same more alkaline rocks, alkaline dikes, because as you thicken the crust, okay, the thicker the crust, more alkalinity will come. So the youngest phases, that is around 1 billion years, very, very alkaline rocks or dikes. That is the latest magmatism that is happening in Tibet now.
So in the Himalaya, you're saying it's just
Melting of the thicker crust.
Okay.
More than 70 kilometers thick. And then obviously opening of the basins in China.
Thank you.
Okay.
More questions?
Thank you so much.
So who's going to go on this trip?
No, there are, maybe I have simplified many things.
Right.
So if I say so complicated story, nobody will come.
Yeah, right.
So you have to come, and then we will talk about more complexities in Kashmir, okay?
This is true about Montana too, by the way.
Yeah, maybe. Yeah.